All right, today we're going to talk about velocity time graphs, but before we get going on that, I want you to think of a scenario where an object has a velocity of 0, but at that same instant it has an acceleration that is not 0. Maybe an acceleration like 5 meters per second or something. So you can go ahead and pause the video for a sec, think about it. I'll assume you've thought about it. Unpause the video. I guess if you can hear my voice, you have. One scenario that I can think of is if I've got a ramp like this and a ball is rolling up the ramp. So I'm going to put some zooming lines here and say the ball has a velocity going up the ramp that way. If it's rolling up the ramp like this and nothing else is touching it, its acceleration is actually down the ramp. Okay, so velocity is up the ramp, acceleration is down the ramp. If acceleration is down the ramp, that means the ball is slowing down. So I'll put less zooming lines here, and by the time we get up here to the top, let's say V is 0. So right at the top. Okay, so at the top, V is 0. The big question is, what is acceleration? Is acceleration 0? Let's think about what if it was. If V was 0 and acceleration is 0, if acceleration is 0, that means your velocity cannot change. It's got to stay constant. So if V is 0 and acceleration is 0, the ball is just going to hang there. We know the ball doesn't do that, right? If you roll a ball up a ramp, it's going to stop momentarily, but then very quickly it's going to start rolling back down the ramp. What that means is this acceleration up here is not 0. The acceleration up here is some number, maybe it's 5 meters per second squared or something. Whatever we said it was over here, the acceleration remains down the ramp this way. Okay, so at that moment, acceleration is not 0, but velocity is 0. It's a good short answer question. Sometimes we ask that one on it.
Ms. Latus, please call extension 400. Ms. Latus, please call extension 400.
Well, there's an announcement immortalized. Let's look at a velocity or a position time graph, sorry. If we've got a position time graph, we know that the slope of this graph gives velocity. And the typical ones that we have done, if I'll just squeeze it on the corner over here. If we've done a position time graph, we've often seen these nice straight line position time graphs. The slope of this line right here gives me an average velocity. Okay, so slope equals V average. What if the line, though, is curved like this one we're looking at today? If the line is curved, there's a couple different slopes, a couple different velocities that I can find. One is I can find the slope of a secant line. Okay, a secant line, if you've never heard of that, a secant line just connects 2 points, any 2 points. It does not need to be the first and the last point, but in my example, it's the first and last. If I find the slope of this thing right here, this slope is going to give me an average velocity. It's the average velocity between whatever the 2 times of the 2 points are. So if this was 0 seconds and this was 10 seconds, then the average velocity that I'm finding is the average velocity between 0 seconds and 10 seconds. Okay, the other thing that we can find from this thing, though, is the slope of what's called a tangent line. Okay, so a tangent line, I'll describe this in one sec, but a tangent line touches only at one point. And if I was to dot that down, let's say, I don't know, it looks like it's maybe 8 seconds. The tangent line, if I find the slope of this thing, and again, I can use any 2 points off of that straight line, the slope of this guy gives me instantaneous velocity, and that instantaneous velocity would be right at 8 seconds. And if you're struggling with what a tangent line is, imagine you've got a pop can in your hand and you lay it down on its side so that you're looking at it from the end. If this is a pop can and you can imagine, I don't know, there's like the little opening is here and the tab kind of thing is there that you open this thing with. That's supposed to look like a pop can. If you were to lay a ruler down on this thing, so the ruler cannot like jam through the side of the pop can, it has to kind of lay on the side. That spot that it touches right there, this would be the tangent line. Okay, so in the one that we drew in the black graph over here, we kind of put it, our graph, I guess, kind of looked like this portion of it, and the spot that we chose was right there. And when we lay our ruler down, kind of missed there a little bit, but if I lay my ruler down, it's going to look something like this. And that line right there is this tangent line that was drawn. Okay, so that's how we draw a tangent line. You can choose any single point. It doesn't, I've drawn two different ones here, but it can be any single point. It's just going to touch at that one point. The slope of that thing gives instantaneous velocity, as opposed to the average velocity that the secant line gives. If I look at position time graphs, then let's go back to kind of a nice straight one. We can talk about converting graphs. If I've got a position time graph and I was to find the slope right here, let's just say the slope, which is average velocity, let's just say is, I don't know, 8 meters per second, something like that. If I find the slope at a different position, because this is a nice straight line, the slope here is also going to be 8 meters per second. And if I find the slope up here, also 8 meters per second. Whether I find the slope during this time interval or this time interval or this time interval, it's always 8. Well, so if I come over here, let's put 8 right here, 8 meters per second. If I was to graph that thing, we kind of said right here at this time interval, I'm up here at 8. At this time interval, I'm up at 8. This time interval, I'm up at 8. I'm just getting this nice straight line here. So the slope of a diagonal position time graph gives me a nice horizontal velocity time graph. So yeah, slope of this thing gives velocity. Just note that if I've got an acceleration, sorry, velocity time graph, the slope of that thing then gives me acceleration. So if I look at this graph over here and I find the slope of this thing, the slope of that gives me acceleration, and you can kind of see that the acceleration from this one, the slope from this horizontal line would be 0. And that makes sense because if I've got a 0 acceleration, that means my velocity is constant. And you can kind of see the velocity is constant for all the times that we've shown over here. If, however, I've got a curving velocity time graph, and I want to find acceleration, remember that's slope, I'm going to find the slope of this thing. Again, there are two different things that we can find. We can find the secant line, so same as we did before, connect 2 points. Again, it doesn't need to be first and last, but it could be. Connect any 2 points, first and last in this case. We draw the secant line. What we're going to find when we find the slope of this line, again, any 2 points off this line, I could be using the first and last points, but use any 2 points off this line. The slope of this thing gives me average acceleration. Whereas if I've got an instantaneous, or if I want to find an instantaneous acceleration, again, let's say, for example, at that 8 seconds again, I draw my tangent line right at that 8 seconds. It touches at that one point. I find the slope of that line using any 2 points off the line, whatever 2 points are convenient. And the slope of that line gives me instantaneous acceleration. If I've got a graph like this, let's say a velocity time graph, and instead of finding, remember slope, let's say slope of a velocity time graph, slope gives acceleration. I don't want to find acceleration in this case. I want to find displacement off of this thing. And what we can say here, let's say we're going to do this for the full 20-second interval. The area between the line and the time axis, okay, sometimes people call that the area under the line or under the curve. We'll hear people say under the line or under the graph. When they say under, what they really mean is what we've written up here, right? Between the line and the time axis. Okay, so if I was to find my line here and the time axis here, it's this area in here. And when I keep going over here, there's the time axis, here's the line, it's this area here. Okay, so if we find those areas, that will give us the displacement. Okay, so that's what I'm going to try to find here. To do that, what I'm going to do is I'm going to break this into kind of some familiar shapes. I want to call this one area 1. It's a 1. It's this area in this section. I'll call this one area 2, and it's kind of this area in this section. And I'll find area 3 here, and that's this one in this section over here. Okay, so I'm going to break it into nice familiar shapes. I don't want to have to try to find the area of a trapezoid, or I forget what all those shapes are, some weird polygons. So I'll see if I can squeeze this down here. Area of that first one, that rectangle, is just length times width. I'll say length is right here, and width is right here. So this area 1 would be the length of, or height is 5, the width is 10. That area is 50. Now let's talk units for one quick sec. Remember this 5, so this 5 going up this way is actually in meters per second. And the 10 going this way is actually in seconds. When I multiply those two things together, the seconds are going to cancel. I'm left with just meters, and that's good because remember what we're trying to find is displacement, and displacement is measured in meters. Okay, so this is not like, probably in your math class you've done this where you said, you know, I've got a fenced-in yard, and this would be maybe 5 meters, and this would be maybe, I don't know, 2 meters, and I find the area, and I end up with 10 meters squared. Okay, that's true, but that's because this unit is in meters and this unit is in meters. In our case, what we've got is meters per second going this way and seconds going this way. Okay, so that's going to give me 50 meters. So that's where those units come from. Last thing before we move on, this direction right here goes right here. Okay, so area 1, 50 meters east. That's the displacement. Area 2, this one now is a triangle, so we're going to say 1/2 base times height, or you can say BH over 2, same thing. Here our base is 5 meters. Remember that's the difference between 15 and 10. So base is 5 meters, height 5 meters. This area, 5 times 5 is 25, divided by 2, 12.5 meters. And again, that direction right there, east, is what goes in here. Let's do area 3. Let's go black up here. And we're going to say area 3, also a triangle, 1/2 base times height. I don't know why I put brackets this time, but anyways, 1/2. Base right here, still 5. The height looks like up to -6. I'm not sure if that's possible. It looks like if it's a straight line, it probably would go through 5, but let's just pretend this thing goes through -6, okay? So the height here, because it's below the time axis, is a negative. When I find this, 5 times 6 is 30, half of that is 15. I'm going to get 15 meters, and again, the direction, east. And like we've done with all of our vectors in the past, if you get a negative east vector, that's the same as a positive west vector. Okay, so I'm actually moving west for area 3. Let's choose a little bright red here. In order to find the total displacement, okay, so this is really what I'm looking for. It is displacement 1 plus displacement 2 plus displacement 3. These guys are all vectors. I'm going to go with all of my east ones. Okay, so there's east, there's east. I'm going to choose the east one here because that's how I add vectors. Okay, so this is 50, and I'm saying east is positive, so 50 plus 12.5 plus -15, because I'm actually going west here, so that's why it's the negative answer. This displacement then, let's see, 62.5. This would be 52.5. I better check this on my calculator, make sure I get this right. We're going to say it is 50 plus 12.5. So that gives me 62.5. Take away 15. That is 47.5. Good thing I checked. 47.5 meters. That is east. Again, because that's the positive direction that we're looking at. We could talk sig digs later, but there is the answer to this thing. Okay, so I started out and I walked 50 meters. Okay, so you could say there's 50. Then I walked another 12.5 meters. Then I turned around and I walked 15 meters backwards, which means in total I am 47.5 meters away from the start. So 47.5 meters east of start. Nice, and that's it.